All right, what's up, guys? All right, you ready for another lesson? All right. So, last time we basically we learned a little bit about how to build your first program, and we went over a few different data types, and all that code is up on the GitHub repository, which I'm going to list at the end of this particular class. Okay, so you guys will have direct access to everything that's been done so far. So one thing I want to really quickly discuss here is so if you look at the code that I have in front of you, I have situated everything based off of the class. So if you look here, everything that was done for class 1 is added under the folder named class 1. Okay. So you'll see all of the code that we did in the last example. Okay, so what I've done this time around for class 2, just to make things a little bit more organized and easy, and I'll be doing this from here on forward, I've kind of put everything into individual class named folders. So what I'm also going to do here, because I just realized this, we probably should name these as what they are. So I'm gonna rename all these to 3. So basically, I misnamed these. I should have put these as class 2 and 3 because if you look at the names of the classes, they were actually class 2 and 3 because class 1 was setting everything up. Okay, awesome. So basically, every single class is going to have a file called the Blackboard, and the Blackboard is where we're going to be talking about all of our individual concepts throughout the lesson, not the individual programs that we create. So we'll be creating some individual programs to go over some of the core concepts of this lesson, but everything that's part of just general notes and general ideologies and concepts we're putting in the Blackboard. So another thing I should really quickly touch on, I'm not going to go into too much detail here, but at the top of each one of these files within the class folder, you'll notice that there's something here called, it says package class 3, okay? And so in Java, there's a concept of a package, and it maps to the folders. So if I were to make a subfolder, let's pretend for a second that make a subfolder called, let's call it folder. Then I could have a package called class3.folder. So I'm not going to do that, but essentially what this does, it allows you to organize your code so you can have files that are named the same in multiple packages. We probably won't be doing that here, but just in the essence of keeping things organized and getting you into the habit of using packages and namespaces, which we'll go over later in more detail. Everything here will be in the class 3 package, okay? All right, cool. So without further ado, I'm going to go over here to my terminal. So in here, I can go into the class 3 folder, right? Whoops. And then I see there's my Blackboard. So I'm going to do Java C Blackboard. Go ahead and compile that. Okay, cool. Runs as expected because it's effectively empty. Cool. And then we've got our generated class file here. All right, cool. So what I'd like to talk about next is the concept of a for loop. So I'm going to create myself a comment block. So if you remember, a comment block starts with a \**, and then it ends with an */. And anything in here is a comment and does not count when it comes to compiled code. So what is a for loop? All right, well, sometimes you want to do a lot of different things in a row. So say you want to iterate over thousands and thousands of pieces of data, and you want to run some kind of a process over each one of those chunks of data. And the same process needs to be done for all of those chunks, but you have thousands of them, right? You're not going to copy and paste the same process thousands of times. You're going to basically feed that data chunk into this process, and that process is going to be written once, and it's going to act on that data chunk so that you can reuse that code to process the data. And that's where, in the grand scheme of things, that's where functions are really, really important, because and they also can be combined with class objects when you get into a lot more complicated program structure. But for now, we're going directly in the for loop and just have the for loop kind of do its thing. And we'll take that example and turn it into a function so you can see how you can create a function that will allow you to reuse that concept later down the road. Okay, cool. So what is the blueprint for a for loop? All right. So for loop basically looks like this. You have the word for, okay? You have open parenthesis, and you have what's called an initialization, okay? And then there's a semicolon, and then after that, you're going to have a condition, okay? And then you're going to have something called an iteration, all right? And then you're going to have a statement, okay? So now I'm going to copy this, and I'm going to show you another way to write this. So generally speaking, you can have a one-line statement, and you can end it at the semicolon, and everything up until the semicolon is completed. So if I had another statement, like here, statement 2, then the for loop would act on this statement, and then this would not be part of the for loop. Statement 2 would not be part of that because it would go up until the ending of the first semicolon. Now, that is not true if you put everything between curly braces. So I'm typing. So this is another way of doing it. So if you have multiple statements on multiple lines, each one with its own semicolon, then you can have them all be part of that same for loop processing by putting them in curly braces. And it is for that reason that I would always suggest, always use the curly braces. Even if you've only got one statement, use the curly braces. Your coworkers will love you better. Okay, cool. Awesome. So what is a condition? There we go again. Bad typing. What's a condition? So a condition is it's essentially a Boolean statement. And what do I mean by Boolean? So, and this is a little bit forward thinking because we're going to go talk about this in the future as well. But a Boolean is the following. So basically, it's true or false. Okay. So you could have something like value less than 10, value greater than 5, something like that. Something that equates to true or false. So if value was 10, this would be false, but this would be true, right? So a condition is some kind of a statement, and you'll see kind of the architecture of that when we do our first example. But essentially, it is just a Boolean, a true or false. So what is initialization? Okay. So it's essentially, man, doing terrible at typing today. Wow. So it's essentially a variable of some sort, right? That is set to an initial value. Okay. So in this case, I'm going to create an integer called value, and I'm going to set it equal to 0, right? That would be an initial, right? So we'd set something that our condition acts upon. Our condition will check every time the loop goes around and round. It'll say, okay, does this satisfy the condition? Okay, does it the next time? Does it the next time? Okay, so but how do we change that? Okay, and that's what is the iteration? So the iteration is updating the value we initialized that the condition checks. Okay? So how does that work? So there's a couple different ways we can do that. This is all getting into a little bit more complex stuff. You can do value equals value plus 1. Basically saying I'm going to set the variable value equal to what value is equal to plus 1. So value is 5. I add 1, and now I update value to 6. There's another one called this, called the pre-increment. Okay? again, a little bit too complicated for right now, but to kind of give you an idea what happens, this actually increments the value before doing anything with it. So in this case, well, let's not make things more complicated, but I'll say that there's two ways that you can do this. Okay, I'll be going over this later. So there's a post increment as well, right? So that's doing the increment after you've said this is the value. Okay, I'll tell you what that means later. Right now is not the time. So these are the three ways that you can increment your value. Okay, so that is the general architecture of a for loop. Cool. So let's go ahead and write one. All right. Cool. So, simplest for loop I can think of. I'm going to say for int value equals 0. Okay. Now I like to put spaces. Some people will do this. Okay. Those people don't like code that looks nice, so I always say do this. Always adhere to some kind of a standard that makes sense and that people like to work with. So we're gonna say value equals 0, right? So that's our initialization, and then we're gonna say as long as value is less than 10, okay, that's our condition, and then we're gonna say plus value. Cool. And then we're gonna do our curly brace. Okay. So now I'm gonna do system.out.println. Remember, that's our printing to the console command. And then we're gonna say my value is, and I'm gonna say %d, but remember I have to put that in a string format block, right? And I'm gonna say value. Cool. So if you look back at the previous lessons, you'll remember how to do that. But now we're going to compile this and we're going to see how it works. So let's compile the Blackboard. Let's run the Blackboard. Oh, could not find class Blackboard. What is going on here? Let's make that public. Huh. Class 3, wrong name, Blackboard. There, to put job on the end of it. Cool. So look at that. Check it out. My value 0 through 9. Okay. So what did this do here? So we're gonna do this so we can kind of look at the program at the same time. Okay. Make sure you guys can see everything I see. Cool. All right. So what we've done is we've set up an integer called value, and we've initialized it to 0. Okay. So what we do is we then execute the code, and we say, okay, the first thing, the condition is 0 less than 10? The answer is yes, it is. Okay. So then it prints out my value is 0. Then when it's done executing this, so basically at the end of this curly brace, it comes back and it says, okay, now I'm going to do the increment part of this, which is plus value. It increments value by 1. And you can, just to be clear, you could do something like fun, like this. And I'm going to add this in here. So this is also equal to plus equals 1. That's another way that you can increment by 1, which means you can do value plus equals 2. So if I were to increment by 2, right? 0, 2, 4, 6, 8. Right? But we're going to change it back to 1. Okay, so we're back to what we had. So the first time it runs this code, it says, okay, cool, my value is 0. Let's increment by 1. So now value is now 1. And it says, is value of 1 less than 10? Yes, it is. Okay, print 1. So it does 2, 3, 4, 5, all the way up to 9, right? So it prints 9. It says value of 9 is less than 10. Cool. I print my value is 9. Then it comes around, increments value by 1. So now 9 becomes 10. It says, okay, value is 10. Is 10 less than 10? No, I'm done. So then it goes exit here. Or rather, for loop exits here. Right? So after it's done, it continues here. Okay? So that's essentially a for loop. Now, this right in here, anything can go in there. You could have thousands of lines of code in there. You could have code in there that takes like a really long time to run through, but it just does a really gigantic piece of logic. But it simply does it thousands of times. So to kind of give you kind of an imaginary idea for what this is, and I'm going to use what's called pseudocode. Pseudocode is not real code. It's code where it's basically I'm just brain dumping ideas. So if I say for my first record, and then I say while I still have records to look at, process record. So move on to next record. So really the pseudocode of this, okay, the pseudocode of this is my initialization is I'm going to grab the first record, okay, and then I'm going to say, oh, okay, cool, I still have records, like I'm not done with my records yet, right? So I'm going to process the record, and then I'm going to, in the increment phase, get the next record, right? And so you could basically just process all kinds of data. And this can be very useful for anybody as long as they have some kind of a process that they need to do automatically. So think about maybe some kind of desk work that you had to do where it was very monotonous and you had to do the same thing over and over and over and over. Well, this is a perfect example for using a for loop, right? Cool. All right, so I'm going to remove that from there. All right, so that's a for loop. Okay. So, let's see here. Okay. Okay. I want to talk a little bit about positioning and formatting, which falls under the realm of code formatting. So, if I had an int x, right, and an int y, okay, then I could do. There's a few different ways that I can present these, right? So I can do x equals y, right? Y equals y plus 1, right? I could even put these on the same line if I wanted to. So let's kind of comment these out, and let's say int x y, right? I can also, or I should also, initialize these, right? So I can do those on the same line. Now, I can't do int u equals 0 double v equals 1. I can't do that because it's a different type. The double would have to be on its own line, okay? So just keep that in mind. You'll get a syntax error if you try to do that. But so I can notate like this, or I can notate like this. I can do, x equals y plus 1, right? So let's add another one in here for more flavor. I can do system.out.println. Right? And I can say, that. But if you take this, you can do that. But I'm going to say this. Note. Don't do this. Don't be that guy. Okay. Let's go ahead and compile that. Pretty sure that works. Yeah, there we go. Doesn't matter what the output is, by the way, but don't do this. Don't be that guy. We never want to see stuff that looks like this. We'd rather see it on multiple lines. Don't ever fall into the trap of the least amount of lines in your code, the better. That's BS. Nobody wants that. Nobody will want to work with you long term if you pull something like that. So here's an example of a method that doesn't fit on one line. Okay, so let's pretend for a second that I'm trying to print out something. Okay, so I'm going to say this is a long line of output. So I do plus x plus y plus z. Well, first of all, I have to probably make a z variable so it compiles. Plus c plus, more output. Now that's really long, right? So now that compiles, right? That's going to compile. That's fine. So it compiles. Also is not spaced very well, but it works. But that's not generally how we want to do things. We want to organize them in a nice, succinct way. So generally what I usually recommend, and this is somewhat of an industry standard, whenever you have multiple parameters to a function like this, and you need to split them up across multiple lines, what you do is the opening parenthesis, you have one line, another line of parameters, and another line of parameters, and you close it off there. And that still works, right? Because Java generally, or any programming language generally, except for YAML and I think Python too, ignores white space. Some languages they don't, but in Java it is compiled. It just kind of throws those out unless they're inside of this string notation here. So all this white space here, all this is ignored. So, okay, so always get into a habit of doing stuff like this. People will be more happy with how you write your code. Awesome. Okay, so code formatting matters. Awesome. All right, so now we're going to move on to our first example here. So I have this class here called gal to lit table, and that's short for gallons to liters table. So I've written the requirements of this here. So this is what we're going to implement. So we've got all the tools that we need, right? And if you remember, gallons, actually I think it was liters equals gallons times 3.7854. Okay, so that's the equation. But what we want to do is we want to display, and we want to essentially print out X number of variations of this from maybe like 0 to, I don't know, we'll start from 0 to 10 at first, and then we'll kind of scale that and make that bigger as we test it out. So let's start simple, okay? So we know that we want to go 10 times in a row, right? So a for loop sounds like the correct thing to do, right? So we're going to create our for loop. We're going to do an integer, and I'm going to call it count instead of value, right? So count 0, right? We're going to say we want to run it 10 times, right? So we're going to go from 0 to 9, right? So do count is less than 10. If you wanted to go to 10, you could do, there's two ways you could do that. You could do is less than 11, so it would early out when it hits 11, or you could even do is less than or equal to 10. You could even start it at 1, right? You could start at 1 and go to 10. So this would evaluate true if count is less than or equal to 10. So once it hits 10, it's still true, but once it goes past 10, it's false. So this is not inclusive of 10. This is inclusive of 10. Okay. So I'm just for, math's sake, to make it easier on the eyes, I'm going to go 1 to 10. So I'm going to use less than or equal. Okay. And then we're going to set our condition, which is plus count. I could also do count plus equals 1, count equals count plus 1, any of those variations. Okay. Okay. Now we have a body. So now the interesting thing here is we're counting from 1 to 10, but we can also use the count variable as our gallon count, right? So if you take this here and you put it in here, why is that not working? All right. So we're trying to output liters. So we're given the input of the gallons. So if we associate this with gallons, right, then we can do the process and we can return or print out liters. So check this out. I'm going to rename this to gallons, right? How about that? So now all we have to do is we can say, and because this is going to be, I believe it's probably better to treat it as a double, right? For floating point precision, and we'll talk about that in a bit. Double liters, right, equals gallons times 3.7854. Now, what's interesting is we've almost virtually carbon copied this entire thing that we have up here. And that's because we took this counter and we named it the same thing we wanted to use in the equation. Check that out. So then we can do something like system.out.println. Okay. And we want to say, well, let's do our string format, right? And we're going to do %d gallons is, and then I'm going to say %f because it's a float. So d is %d is for integers, %f is for floats. %f is liters. Okay. And then we'll go ahead and plug gallons in here and liters in here. So let's close off that parenthesis. And just like we did before, you know, I'm going to do this to make the format better. Okay. So let's go ahead and run that and let's see what happens. All right. So we're going to Java compile that. Cool. That worked. Let's run it. Cool. 1 gallons is 3.7. 2 gallons is 7.5. We're going all the way up to 10. Okay. Cool. Now, if I want to do 100, I have to do this, right? Just change that number there to 100. So let me clear the screen. Let me compile it again. Let me run it. Whoa. Look at that. I've done all the calculations from 1 to 100. Okay. And I could easily do, you want to go crazy? Let's try 10,000. Look at that. I've literally printed out 10,000 lines to my terminal. Now you can see the power of programming when you write something that can be reused. Now, this isn't quite reusable yet because, well, this is just a chunk of code. So anytime we want to use it, we're going to have to copy paste this, right? We're going to have to run everything through this program, and that's not really the best way to do it. So I'm going to call this the standalone for loop, okay? And there's nothing wrong with this, by the way. Not at all. Standalone. But this is where I would actually do refactoring here. So, how do I want to do this? A couple things. I'm going to create, I think I can do a private static. I'll just do a private static. So the first thing I want to do is I want to put, actually, let's copy and paste this, right? And let's get rid of everything we did internally, okay? And we're going to call a function here to do the calculation, okay? Because I don't want this code to have to change in multiple locations. I think we should only ever have to write this code once, ever. So I do private static double, because it returns a double. And I'm going to say gallons to liters. It takes in, whoops, breaking stuff over here. Let's see, final int gallons. Now, what's final? Final means that you're not going to change this value. So this value gets passed in, but you can't modify it. It just basically says that nothing within this method is allowed to modify it. And it's a really good habit to get into that habit. To get into that, get in the habit of doing that, because it's better to specify that you're not going to change it. And then if you realize you are changing it, then you can sit there and be like, do I really want to change it? Or do I want to do it a different way? Because if you start haphazardly throwing your variables into functions and you don't protect yourself, somebody else will break your code later down the line, and you'll have to fix it. Okay, so essentially what we're doing here is we are wrapping our logic. So we're going to take this, okay, and we're gonna say, okay, I know that that's the code that I wrote to calculate liters. So really what I'm gonna do is I want to return liters. So I can do this and return liters, right? But I can also do this. So I'm going to leave both versions so you can understand right there. I'm going to return gallons times this, and there it is. So essentially what I get to do here is I get to pass in gallons. Right? So what I can do from there is there's a couple different ways I can do this. So I can do double liters equals that. And then I can kind of see if I can line that up. So I can do this, right? Or what I'm going to suggest you do is you can get rid of this entire line here. Right? So you know liters is equal to this, so you can actually just replace this with this. And then reduce this. So let's bump these back down to 10. Right? Let's compile again. We should see 2 for loops being printed out of the exact same value. Yep. They both do the same thing. Okay. This one is slightly better than this one, but only by 1 line. Right? But the nice thing is we have this function here that never has to change. We can call this anywhere in our entire application and it never has to change. This is really extensible. Really, it's reusable. Okay? So we're going to do a little bit more because I want to format this and make it really, really nice. Right? So I'm going to comment this guy out. We don't want that showing up in our output anymore. Right? So essentially, we're going to compile it, and we're going to show just 1 through 10. Cool? All right. Now, part of the requirements I have is that I want to be able to, I want to make a table, right? I want to make a table. And so to do that, I want a divider line up here, right? I want a divider line of dashes at the top, and I want a divider line of dashes at the bottom. In fact, I'm going to go further and say I don't want dashes, I want equal signs. So I want it to look something like this, right? I want it to be really long like this. Okay, so what do? Well, I just copy my print format line, all right? And then I do that. I can copy that same thing, and I can do that, right? And let's just say, for instance, that I want to add a couple spaces before all of my lines to give a little bit of an indentation. In fact, I'm going to show you a trick. \T. This is actually an escaped character, so it doesn't print the letter T. What it does is it inserts a tab. So check this out. So we're going to compile it again. Cool. Look at that. Looks better already, right? Cool. So now we're getting into something that's pretty on the eyes that you don't mind looking at. And if you have lots and lots of records that you have to process, you want something that is going to be easily viewed and sorted through. Okay, so I'm going to take this another place. What I'm going to do is I'm going to take this whole thing here. I'm going to put it in a function. So I'm going to do this. Whoop, this one is not going to return anything. I don't believe it should return anything. We'll change it if we have to. But I'm going to say print gallons to, get out of here. Print gallons to liters table. Okay? All right. And then what I'm going to do is I'm going to copy all of this. Okay? I'm going to put it in here. And then I'm going to start thinking through it. So when this function gets called, which I'm going to call right here, call one function to do the magic. All right, let's think through this a second. So when I print out my header line, and then I know I'm going to start at 1 gallon, and then I'm going to count up to 10 gallons, okay? So get rid of this. And we're going to print this guy out. Let's go ahead and reline this because this got messed up. Okay, so we're doing everything we did before. Okay, awesome. So essentially, this should be a nice consolidated way of doing things. All right, so let's... Cool. So now we have a method that prints our gallons to liters, and we have a method that prints our gallons to liters table. Now there's one small optimization I'd like to do to this to show you an even better power. And that is, this 10 here is a magic number. Magic number is something that's hard-coded that may need to change later down the line. What if I wanted to call this function, but I wanted to call it one time with 10 and another time with 5,691 for some dumb reason? Well, then I'm going to do a final int max gallons, right? And I'm going to do this as long as gallons is less than or equal to max gallons. And then I can just, put the 10 in there. So once again, we're passing 10 in there. And then we're using that to tell our for loop what to do. Ta-da. Nice, huh? So let's do 100. We change it in one place. Let's compile that again. Let's run it. 100. Okay. So this is what's called refactoring your code. So we did it the long way. We then sort of like worked backwards and made it a little simpler, and then we ultimately made one function that did everything, and we just kind of reverse engineered everything down. We distilled it down to its simplest parts, separation of concerns. So this is the logic layer, which does the math calculation, and this is the data printing layer, which actually goes through a range of data values and then processes them in the for loop. Cool? All right. So before I move on to some of the other concepts of this lesson, I want to go over really quickly a couple things about reserved keywords. Okay, so you've already seen these orange words in here before, and there were quite a few of them that we saw, back in lesson 1. And we'll go over a lot of these later on, but I'm going to talk about the one specifically that we've seen today. So package, that is the package that this file lives in. And in this case, it's the folder class 3. This is reserved. You can't name a variable named package. Same with class. You can't name something with the name class. It is reserved. Same with public, private, protected is another one, static, void, double, int, float, char, boolean. There's a few that you'll learn along the way. Keywords like back in lesson 2, we had if, else. These are all reserved words that you are unable to use. And then obviously your for loop. Okay. Return is another one. So anything that is specific to the language of Java itself, and this holds true for any programming language, you cannot name anything based off of reserved words. So another thing should probably touch on. That's the wrong file. So some special reserved keywords that I'd like to make sure you're aware of is true, false, and null. So when we learn about booleans, you'll figure these out, but true is true, false is false. Null is a special value, which means it's zero memory. It means that the underlying memory address points to nothing. And we will go over what memory addresses and pointers are later. Right now is not that time. So just keep in mind that null is sort of like pointing at a black hole. It means absolutely nothing. And that can be important for various reasons. Okay. Cool. All right. So moving right along. So let's start talking about data type primitives. Okay. So we have the following data types that are primitives, okay? We've got Boolean, byte, it's an 8-bit integer, okay? Got char, double, float, int, long, and short, okay? I don't expect you to know all these off the bat. We're going to be talking about basically integers and floating point numbers today, and that's as far as we're going to get. We're going to talk about the other ones later. I do want to go through some of the integer types now. So we're going to go over some theory. This is some important things to know moving forward. You can go pretty far without ever knowing any of this stuff, but if you understand it and you kind of keep it locked away up here, it'll definitely prove its weight in gold later on. Okay. So what are integers? Well, they are whole value types. Okay. So we're not talking about like 3.12 or 5.189. We're talking about 1, -20, 350, 10,165. It's just whole numbers, no decimal places or anything. The first one we start off with is the byte, right? So a byte is 8 bits. And without getting into actual binary and how that works, I talked about the value of 1 and 0, which is effectively binary. The electrical signal is either on or off. This means there's 8 wires in a row, and they're all turned on and off in multiple different combinations. And if you were to break that down mathematically, you would be able to figure out that the minimum value that you could represent with 8 bits is -128, and the maximum value is 127. And while that sounds like, oh, I don't think I'll ever need to know that, yeah, there would be points where you would, and if you know how to figure out the limits of particular variables, you will save yourself a lot of time, and thus the company time, and therefore money. Because what happens if somebody wrote some code where they're storing some data, and turns out they're losing precision, and they're trying to figure out why their numbers aren't coming out correctly? Well, it could be because they're using a data type that was not large enough to hold the amount of data that they wanted. Generally, in today's age, you just use whatever seems like a pretty good container, like whether it's byte, int, short, long, etc. In the old days, people would exclusively use the shorter types. Like if you knew you were only going to store something from 1 to 10, you stored it in a byte because space was expensive. Nowadays, space is not so expensive. If you're dealing with robotics, or you're dealing with things like watches, or like really, really small embedded systems, you're definitely going to want to get into actual smaller data sets and be very frugal with what you use. So moving forward, we have a short, and a short is 16 bits. Okay, and that can go from 32,768 to 32,767. Okay. Then the common one that's used is the int. Okay, the int is 32 bits. Okay, that one can store a heck of a lot more. That's 2,147,483,648. That's negative, right? And that goes all the way up to 2,147,480. Ooh. 647. And then we have what's called the long. And that's if you really need a lot of space. And that doubles the amount of space from before. So that's 64 bits. So if you heard of a 32-bit versus 64-bit, whenever you're downloading something, it asks you what kind of processor you have. And that's exactly this. Does it support ints or does it actually support longs? And all the newer software out there supports longs. And that's important because you would want to develop software that can handle that. So this is actually quite ridiculous. This is 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854,000 or million, sorry, 775,808, and that goes all the way to. And what we're gonna do is just copy this, make it positive, drop it by 1. There you go. That's it. You don't have to memorize this, by the way. Don't worry about that. What I would say is just know 8, 16, 32, 64. That's about it. And as long as you know around 2 billion something is what an int can hold max, either negative or positive, then you can kind of decide, do I need more than 2 billion values? And if so, then you're going to want to go for a long. So really, just knowing these 3 thresholds will allow you to infer this threshold, because rarely anyone needs this kind of precision here. So just get used to knowing these 3 down here, and knowing they double from 8 to 16 to 32 to 64. So it's always a multiple of 2. 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64. All right. So those are all of our integer types. Okay. So now we're going to go over and we are going to create a program. Okay, we're going to compute the number of cubic inches in 1 cubic mile. All right. All right. So let's think about this for a second. Okay, cool. So first thing we know is that, cubic mile, so we're going to write out some notes. Generally, you want to think things through. So you say, okay, work backwards. I have a 1 cubic mile. So I know that a cubic mile, right? So a cubic mile equals, it's a mile times a mile times a mile, right? It's basically a mile raised to the 3rd power because it's cubed, right? Okay, awesome. Then we got to think, okay, so what's a mile? So a mile is, a mile equals 5,280 feet. The answer. But I have some notes, so I'm going to tell you that a mile is 5,280 feet. Okay. So then we're going to work backwards and say, okay, what's feet? So we know that So this is 1 mile equals that amount of feet. 1 foot is 12 inches. Okay, awesome. So now we can kind of work backwards and we can say, okay, we're going to compute the number of cubic inches. All right, cool. So there's a bunch of different things that we're going to need. So we know we're going to need to calculate a mile. So I'm going to use a long because we don't know how much we're going to try to calculate. We could try to do something crazy here. So we're going to say long foot, right, equals 12. Okay? Okay, so a foot equals 12 inches. So we're just going to say 12. Okay? Then we're going to say long mile. And what I'm going to do here, just to take my notes and kind of organize them is I'm going to do this. Okay, and you can kind of tab these over to make room. Okay, so I'm also going to say I'm going to be working on this guy right now. So I'm going to say, okay, 1 mile equals 5,280 times a foot, right? Okay, let's get rid of this guy because I don't need that one now. So then we're going to say, all right, well, now I want to say long cubic inches equals, and that one is this guy. So now we're going to say, what? That's mile times mile times mile. So we're literally going to say, and I'm going to move all these over. Okay. Okay, so let's walk that backward. All right, so we wanted to compute the number of cubic inches in 1 cubic mile. So we say there are 12 inches in a foot, so we define a variable called foot set to 12 for the number of inches in a foot. So 1 foot is equal to 12 inches. Then we say, okay, I want 1 mile, and I know that there are 5,280 feet in a mile, so I take 5,280 times foot, which is really 5,280 multiplied by 12 inches because there's 12 inches in 1 foot, right? And then I take that mile and I cube it, and I get my cubic inches, okay? So what I can do is print that out, and I'm going to say there are, and I'm going to do the string format again, right? There are %d cubic inches in a cubic mile. And I'm going to go ahead and put the second parameter of that on another line. Okay. All right, now let's try that out. Java C, inches. Aha. Identifier expected. That's right. What am I doing? That's what I get for working all day. You cannot use a comma and a number. Most of you probably already knew that already. Cool. There we go. Java inches. Cool. Wow. What is that? That's 1,000, million, billion, 254 trillion, 358 billion, 61 million, 56,000 cubic inches in a cubic mile. That's a lot. There you go. Cool. And you could also data drive this. You could say, you create a function called, how many cubic inches in X cubic miles, and this number would explode drastically. So, cool. So that's integers, and that's one instance of why using a long makes sense, right? Because you wouldn't be able to store this data in this answer in here in a normal value. See how long that is? That's in the trillions. Whereas, what we went over on the blackboard here, we talked about int only goes up to billions when we needed trillions. So we had to upgrade ourselves to use a long. So there's a good instance of that. Cool. All right. Let's see. What are we going to do next? Let's talk about floating point numbers now. So let's go back over to the blackboard. All right. All right. So floating point. So, and these are real numbers, right? So essentially, there are two types right here, and give me 2 seconds. I want to pull something up here. So we have two floating point types. We have a float. Whoops. This one is 32 bits. Okay, it stores 32 bits worth of data, and there is no range, right? Because it could be anywhere from like some really large number with like a couple decimal points, or it could be like 0.000000 and like a bunch of low-end decimal points. So it just depends on what kind of precision you need, and by precision it means how many decimal places do you want to support for this value. So really it matters of, do you want 32-bit precision or 64-bit precision? If you are dealing with physics or any kind of measurements that deal in nanoscale, like a lot of this virology or epidemiology that they're doing right now over the coronavirus, you're going to want to use doubles because you're going to want as much precision as possible. So that was 64 bits. Cool. All right. There's not a whole lot that I can really go over here because we've done some stuff with floats and doubles already. So this is sort of review. The most you're going to get out of this is the difference between 32 and 64-bit and what the difference between float and double is. And that's it right there. So now I'd like to kind of take you into an example where we do another little exercise, and we're going to resurrect the the hypotenuse. Right? And so everybody's like, oh no, I hate math. You know, programming makes you understand all those simple math concepts you studied way back in the day and hated. It helps you understand them, and when you solve them, you write them once and you never come back. And then you, not only did you solve them, but now you understand them, and you can kind of put everything together to solve complex problems. Because math in general was all about learning tools that you could use to solve other problems. Like if you ever took physics, you could start to solve real world problems and do predictions based off of, you know, if you threw something at a specific angle at a specific speed, where is it going to land if it's going that direction, and gravity's all this, blah, blah, blah. And that's exactly what programming allows you to do very quickly. You write the formula out in code, and you have your computer do it. So you can have it run simulations based off of a bunch of different random situations, and you can do some really cool stuff, especially if you put that behind a rendering engine, graphics engine, and then you can kind of say, okay, show me a ball getting thrown out and doing that whole like throw it up in the air, or where's it going to land at various speeds, and you could just do all these crazy fun simulations and see where you. So all right, awesome. So what is the Pythagorean theorem? So the first thing you want to do is you want to figure out what is that. Okay, so the answer was the hypotenuse, right, equals and I don't know how to draw the square root, so I'm going to do like square root, and I'm going to put that in parentheses because that's all I know how to do. So we're going to take the square root of, I believe it was x times x, right, plus y times y. And I usually put things explicitly inside parentheses, so it's, you know, pretty clear what needs to be done. Okay, so that's our equation, and so we need to turn that into an actual formula and print that out. So, okay. So basically, I'm going to declare 3 doubles because there's 2 doubles that are x and y, and a double called hypotenuse. So remember, I can do double x, y, and z. I can declare them all at the same time. And I'm going to say x equals 1.0 actually. Let's say y equals 1.0. okay? And then we're going to say, well, I'm going to change z to be hypotenuse, right? And I'm going to say hypotenuse equals, okay, well, how do I do the square root? Well, guess what? Google. How to perform a square root in Java. Tutorials point. What is this? java.lang.math.square-root. Cool. So I think that I could just... Let's see if I can just do this. Yep. Okay. So should be something along these lines. Math.square-root, and then you do x times x plus y times y. Now let's see if that compiles. Oops. Looks like it compiled. Okay, cool. So, all right. So we'll do system.out.println and say hypotenuse of, well, let's also remember string.format of %f, %f, and %f is %f. And then we'll go ahead and do this on multiple lines. So we'll do x, y, hypotenuse. Let's go ahead and there. Okay. Oop. Cool. So the hypotenuse of 1 and 1 is 1.414214. Cool. So now this is a lot of code. I don't want to write that much code. So I'm going to consolidate. So remember what I said about writing functions? So we want to take all of this and put it in a function. So we're going to get back the hypotenuse. So we're going to do private static double, calculate hypotenuse, and we're going to take in the x, and we're going to take in y. Whoops. Okay. Now I'm going to copy. I'll paste it here. I'm going to take this. I'm going to say double hypotenuse equals that. And then, cool. However, I'm going to clean this up even more. Haha. I'm going to say I can just return the hypotenuse, right? I can return it, so I don't need to declare it. I can also set these in here and get rid of these. Actually, no, I don't need these at all because they're being passed in. Right? And I'm going to take this comment here and move it up here so that my calculate hypotenuse function becomes simply this. Okay? And then I'm going to take this print out here and I'm going to say, okay, I actually like the idea of having the x and y up here on this line, and I'll keep the hypotenuse on the second line here, that parameter. But then I can also take this whole thing and I'm going to cut that. I'll put it there, right? And get rid of this. Okay, there's my string for the string formatter. I have 3% f's. The first one is the x value. Next value is y. The next value is calculate hypotenuse. Strangely, though, we still have to I should have recognized this, but we're still going to have to declare these here. And just pass in x and y straight up, okay? And I'm gonna fix this in a second, but basically, there it is. So let's compile that again. Cool, same result. But now, here's what I'm gonna do. Do something really, really funky. Remember this guy? Print gallons to liters table. Check this out. I'm gonna repurpose this code. I'm gonna copy that whole function. I'm gonna go over to my hypotenuse file. Right? I'm gonna paste it here. Let's go through it piece by piece. A private static void. Some water. And I'm gonna say print hypotenuse table. Okay. And I'm going to say we're going to go with max side length, I guess, right? Because that's what we're really using to calculate the hypotenuse. Okay, cool. So we're going to print the same line we did before, and we're going to say in gallons. Nope, we're going to say side length, right? So we'll replace gallons with side length. And then max side length, so we're going to replace max gallons with max side length, okay? So let's read that. For side length equals 1, we'll make that 1.0, right? And also, it needs to be a double, right? So does this. All this needs to be doubles, because we're operating on doubles now. So the double here is max side length. So for double side length equals 1.0, side length is less than or equal to max side length plus side length. We do a bunch of stuff in here, and we print out the exit line. Awesome. The guts of it says print a line, the string format, %f side has a hypotenuse of %f. Okay, so the values we need for that is side length, right? And then we need to call calculate hypotenuse here. So what it really reads is system.out.println string format tab %f side has a hypotenuse of %f, whereas the first %f is the side length, right? So that's effectively our counter. And then our calculate hypotenuse method is called inline right here, and the result is plugged into %f, and we calculate it with side length. So we're going to do 1 times 1, 2 times 2, 3 times 3, 4 times 4, all the way up to whatever max is. So if max is 10, we're going to print out a table all the way up to 10 times 10. Cool? So now, let's do this. Let's chuck all this. Let's say we want to print out the max of 10. Now let's compile that. Okay, let's see. Method calculate hypotenuse in class cannot be applied to given types. Calculate hypotenuse. Because we have to pass in side length twice. Okay. Cool. So you notice how calculate hypotenuse takes in double x and double y. So we're just passing in the same value twice in a row. Okay. So we compile it. Let's run it. Ta-da! All the hypotenuses from 1 to 10. 1 times 1, 2 times 2. Cool. So I didn't really go over that much there today. Mostly what I went over for you guys is for loops. So we've done a few examples of that. I've gone over integers. I've gone over floats. And then I've also gone over how to start from the raw idea, the pretty rough idea of what you have to work with, and then, you know, get something working, and then work backwards to kind of streamline it and turn it into something a little bit more pretty. So we started by just kind of putting everything in the main function, and then we said, okay, well, let's take the calculation itself out. Let's make a function so that it's nice and prettified. And so once we got that taken care of, we updated the original. And then what we did is we took this printing out logic to do our table that prints and calls the actual function that calculates, and then we drive this by one number to kind of do everything we want it to do. So our main code, if you see, this is kind of the beginning stages of what you're going to learn in software engineering, where you take your idea, get it working, then you you take it backwards into a more refined approach. And so this is kind of how you do that. So you kind of just reverse engineer it so it's nice, one single function. And that's kind of the goal, is to turn everything into one thing. That's the unification, living in a beautiful world kind of thing. So everything is just simplified. Okay, cool. So, all right. So that's it. That's a little bit shorter than the other lectures. I'm trying to make sure we stay on top of keeping things about an hour or so. And so that's kind of where we're going to be from here on out, unless we go into some stuff that's pretty verbose, and I'll let you guys know ahead of time if I think that's coming. All right, cool. So that's it. I'm going to be heading over to the Zoom chat. So go ahead and click the link in the event page chat, and I'll be there in about 5 minutes or less. All right, I'll see you guys.